All right, thank you so much. First of all, it's been a real pleasure to be here. I think on behalf of the whole Dark Matter workshop, we've had a great time. We're only halfway through, so we'll be around and really happy to also interact with the other program that's here. So if you're at the wonderful talk last week from the Plasma and Kinetics program, there are a couple differences. So there's only one of me today. There were two presenters last week. And we also heard the definition, at least in the context of the Plasmas workshop, about what is a galaxy. And I'll give you the dark matter view a little bit later on. Okay. So the purpose of this program was to bring together theorists, observers, and simulators who are working on the problem of dark matter. And this is a really exciting time for the field because we have a flood of new data coming in, particularly regarding the distribution of structure in the universe, which is one thing I'll focus on in the talk. And we believe that we'll be able to really advance our understanding of dark matter even within the next decade. So I hope to convince you of this. But before I go into the details, I wanted to start with sort of a bit of a historical view, just of some of the most robust evidence we have for dark matter, where this idea came from. And many of these themes are going to come up throughout the talk, so I wanted to start there. So let's start with evidence for dark matter. And this is a long and rich story. The history is actually fascinating, I think. But I want to start in the 1930s. So this is when Fritz Zwicky and actually many others were observing clusters of galaxies. And based on the motion of the galaxies within these large clusters, we're able to infer that there was much more mass than was accounted for by the visible matter alone. So the picture to have in mind here is that there's some large collection of galaxies sort of orbiting around each other, each with some velocity. And what Zwicky did was pretty clever. He applied the virial theorem to this system. So he said that for a self-gravitating system, the average kinetic energy should be related to the average potential energy, which, if the only force law is gravity, has a simple coefficient of 2 here. And so if we expand this, if we think about the velocity dispersion of the galaxies within this cluster, there's a simple relationship between the total amount of gravitating mass and the velocity dispersion of these galaxies. And what Zwicky observed was that the measured velocity dispersions were on the orders of thousands of kilometers per second, whereas the expectation just based on the amount of luminous matter was on the order of 80 to 100 kilometers per second or so. And this leads to the conclusion that the total amount of mass, so total amount of mass is roughly equal to 500 times the amount of luminous matter, for example, in the Coma cluster. So this was a very striking result at the time, like I said, almost 100 years ago. But since this result, in the kind of coming decades afterwards, not so much happened. There was actually a lot of debate about this in the literature. There was actually a famous conference in Santa Barbara in 1961 where folks debated about the interpretation of this measurement. Maybe the clusters were not dynamically stable. Maybe there was some other mechanism that was preventing them from essentially flying apart other than a bunch of matter we couldn't see. Okay. So the next big step in this history was the measurements of galaxy rotation curves, particularly in the 1970s. I'll focus on the measurements from Vera Rubin and Kent Ford. But there were really many other people working on it at the time. And what they observed was the rotational velocity of stars and gas as a function of the distance from the center of a galaxy. So if we consider, for example, our neighbor, the Andromeda Galaxy, and we plot its rotational velocity profile as a function of distance from the center, the expectation from Newtonian gravity is that past the visible extent of the stellar and gaseous disk, the rotational velocity would fall off, and this power law drop-off is just given by Newtonian gravity. It goes like r to the minus 1/2. But this is not what people observed in the 1970s. Instead, the measurements of the rotation curves looked more like this, where in the inner regions, the motion was measured directly from stars. And in the outer regions, these were radio measurements of H1 gas from which the rotation velocity could be derived. So again, the conclusion here was that there was much more gravitating matter than there was luminous matter in these galaxies. For Andromeda, for example, there was a factor of about 10 excess. But this held for many galaxies. In fact, tens of galaxies had precisely measured rotation curves at this time. And the conclusion was becoming more robust that dark matter exists in galaxies today, pretty much in every galaxy we knew of at the time. And so the question, of course, was, what is it, right? And we still have that question today. Now, one of the issues with the interpretation of these early measurements was that astronomers were not sure whether the dark matter might just be some other kind of mass that's too faint to observe, but nonetheless, something within the standard model of particle physics. For example, very faint stars or compact objects. And I'm going to skip a few decades. I'm going to come back to the story of cosmic structure. Yeah, there's a question.
So is the factor of 10 kind of the same in every example, or just different galaxies?
Yeah, so there's definitely scatter. It depends on the mass of a galaxy. So one thing you might already notice is that this factor of 10 is much smaller than this factor of 500. That's actually not too unreasonable given our kind of modern understanding of the amount of halo mass in each galaxy. I'm going to come to this in detail later, but there's certainly scatter. Nonetheless, most galaxies needed a good amount of dark matter. Yeah. Okay, so I'm going to skip a few decades and come to the measurement that really kind of sealed the deal, I think, for the interpretation of dark matter as something outside of the standard model of particle physics. And these were the measurements of CMB anisotropies, which again has a long history, but I'm going to focus on what happened in the early 2000s with telescopes like WMAP and then later Planck. The idea here is that we observe cosmic microwave background radiation coming at us from all points on the sky. It's very cold. It has a temperature of 2.73 degrees Kelvin. But crucially, the amount of variation from point to point on the sky in the temperature of these cosmic microwave background photons is extremely small, one part in 10 to the minus 5, right? So the early universe, when we observed this light from the surface of blast scattering, the universe was extremely smooth. But crucially, as I said, starting in the early 2000s, the angular structure of the correlations in this temperature field started to be measured. So what we can do is plot as a function of the angular scale essentially the amount of temperature fluctuations. And there is a prediction for this spectrum of temperature fluctuations from a standard cold dark matter paradigm that looks roughly like this. So the angular scale of this first peak in the CMB is roughly 1 degree. You can think of this as telling us roughly the total amount of matter in the universe, whether it's dark or not. This is compression, right? This is gravitational compression, condensing the photon baryon plasma in the early universe. This second peak is rarefaction, so the photons exert pressure on the baryons and they oscillate out of their potential wells. So you can think of the height of the second peak relative to the first as telling us about the amount of baryonic matter. But the crucial detection was actually the height of this third peak relative to the second. And this tells us about the residual contraction that the gravitating mass is doing. And of course, that gravitating mass is dark matter, right? It can't be baryonic particles. So this story that I've told you, up to this point has illustrated a few things. There's a lot of dark matter in the universe. The measurements from the CMB imply that 85% of the total amount of matter is dark. It has to be stable, and it has to be cold and collisionless on large scales. Otherwise, this spectrum of temperature perturbations, which I didn't even attempt to plot the error bars on because they're very small and they fall right along the curve, would be messed up. Okay, so with this in mind, now I want to turn to a more sort of modern picture of what the dark matter is doing. And this has to do with the formation of structure in the universe. All right. So the way that we describe the distribution of dark matter, I'm going to write just a couple equations to give you the idea of what we do, and then I'll turn purely to plots. The way that we describe it is through this matter over density, fractional matter over density. Which is essentially, from point to point in the universe, how much excess matter is there relative to the cosmic mean. And what we can do is write this as a Fourier transform. Where the Fourier modes of the density field are a function now of the wave number k instead of the physical scale x. So you can think of large wave numbers as corresponding to small physical scales and vice versa. The key quantity that we measure is known as the power spectrum, which is essentially just the squared amplitudes of the Fourier modes of the density field. All right. So I want to show you how this looks. And this is a plot that I will return to a few times, so I'm going to try to make it pretty big. So I'm going to plot as a function of this wave number k, and I'm going to put some units here just for reference, because I'll fill in certain values. I'm going to plot something proportional to this power spectrum. Actually, it's a dimensionless version of the power spectrum, k cubed times p of k. And I'd first like to put the prediction from a model where dark matter is really boring and it only gravitates. So dark matter is cold and collisionless on all scales. This is not a realistic model of particle dark matter. All models will break this assumption, but it's informative to look at. So this is the prediction assuming, as I said, the dark matter only gravitates and that there's a roughly scale invariant spectrum of density perturbations in the very early universe. All right, so you'll notice a few things here. First of all, this curve sort of inflects. This point, which I'll label as roughly a wave number of 0.01, has to do with the redshift, or the epoch, at which the universe transitioned from being radiation-dominated to matter-dominated. So modes that entered the cosmic horizon while the universe was radiation-dominated grew more slowly than the modes that entered when the universe was matter-dominated. So one just kind of informative way to read this plot that you can remember throughout is actually from right to left instead of from left to right. That's how I like to read it, because time is moving this way as the cosmic horizon grows, right? Okay, so there are measurements on large scales, as I said, from the CMB, from the large-scale structure of galaxies that are consistent with this CDM prediction on large scales. But our methods need to change when we approach smaller scales. So let me mark a few more interesting points here. So this wave number of 0.1, yes, question?
Small k, right? And it goes to zero at small k in this picture. So is it consistent?
So these k's here are extremely small. So these scales are comparable to the size of the universe. I'm going to show you where individual galaxies map onto this plot, and it's at much smaller scales than what I've marked so far. Yeah. Okay. So something interesting happens at 0.1. If we take the expectation for the size of the density perturbations that entered the horizon here and ask how large are they today, it turns out that these are the largest self-gravitating halos that exist in our universe today. So essentially bound, gravitationally bound clumps of dark matter. So these we refer to as largest galaxy clusters. So the largest halos in the universe today have masses of roughly 10 to the 16 solar masses. There's a useful mapping between the mass of a halo that forms and the corresponding wave number k. I'm going to write it down just for reference, so you can think of this as being set by k to the minus 3, just dimensionally. And this turns out to be 10 to the 10 solar masses, k divided by 10 to the minus 3. And I'm going to come back to this a few times. Okay, so we have measurements of the power spectrum on these scales. They become less precise than what we have on very large scales. There are techniques, for example, using the Lyman alpha forest to trace density perturbations at relatively small scales. But for modes that are much larger, for wave numbers that are much larger than 1 inverse megaparsec, so smaller scale density perturbations, we sort of currently lack model-independent measurements of this power spectrum. And this is the region of the plot where I want to argue that there's a lot of interesting dark matter physics to discover. So around K of 1, if we map these to halo masses, correspond to the halos that host galaxies today. I'm going to keep going a little farther so that I can mark the region of this plot past which we expect halos to remain completely dark, in other words, not to host galaxies. So this, as I mentioned at the beginning, this is our definition of what is a galaxy. So we refer to systems of stars and gas whose motion can't just be explained by Newtonian gravity as galaxies, right? So still keeping the 1/r potential from the plasma and kinetics talk, but crucially adding dark matter. So halos to the right of this roughly K of 100 or 200 boundary, we expect to remain completely dark. We have to detect them through purely gravitational means. And so I hope what you can see is that there's a large and interesting discovery space here, right? The CDM curve I drew is just an extrapolation of what we've measured on large scales, and if dark matter does something interesting on these scales, then we can detect it using structure. So I'm going to give just a couple examples of the kinds of interesting things dark matter can do on these scales. And I want to just sketch out the basic physics of these different scenarios. So the first class of dark matter models that I'll consider is known as warm dark matter. This is just a placeholder name. In fact, we've been arguing about whether this is a good name to use during the workshop. But really what I mean by warm is that the dark matter particles, instead of being produced cold, they're produced with a non-negligible velocity dispersion. So they stream over fairly large distances as structure forms, and this wipes out the formation of small-scale structure. So I'll just draw sort of an illustrative warm dark matter curve on this power spectrum. You can actually understand fairly simply what sets the scale, right, for the wave number where this power spectrum cuts off. And it's just related to the velocity distribution that the dark matter is produced with. So this is some integral over the sort of initial thermal velocity of the dark matter particles from a very early time until gravity takes over and the modes just grow due to gravity. So this is one possibility, right? If we detect, for example, a cutoff in the power spectrum corresponding to a lack of small-scale structure, then it might be due to the free streaming of dark matter particles produced in some interesting way. For example, models of sterile neutrino dark matter sort of generically have this physics. But there are other possibilities that can affect structure on these scales. So to give another example, I'll introduce what we refer to as fuzzy dark matter. I think there's also some slight question over whether this is a good name, but hopefully I'll show you it's at least descriptive. So in this case, unlike the warm dark matter paradigm, we're considering dark matter particles that are extremely light. So in particular, the de Broglie wavelength of these particles, which is inversely proportional to the mass, becomes extremely large, right? And if we make the particles sufficiently light, then this de Broglie wavelength actually becomes macroscopic in size, of the order of the sizes of galaxies. And this, again, leads to a characteristic cutoff in power spectrum. The cutoff actually has a rather different shape than that in warm dark matter. But nonetheless, the effect is still to suppress small-scale structure. OK, so these are two possibilities. And one final one, just to show you what a wide range of physics we can probe, is known as interacting dark matter. Again, here the name is a little bit tricky because warm dark matter and fuzzy dark matter can also interact. But here what I mean by interacting dark matter is dark matter particles that have a large scattering cross-section with the standard model, for example. So imagine dark matter proton interactions with cross-sections that are fairly large. Then again, there's a characteristic scale at which density perturbations are suppressed. And this can be understood from collisional damping. So I'll write the collisional damping length. And this is roughly proportional to the size of the cosmic horizon when these interactions freeze out. And I'm happy to talk about this in detail if people have questions. So once again, there's a signature in the matter perturbations in these models. I drew it with some fairly large oscillations. These should remind you of the oscillations we saw in the cosmic microwave background spectrum. It's really the same physics. The dark matter is tightly coupled to baryons in this case, so it oscillates following what the baryons are doing in the early universe. Okay, so there's a wide range of possibilities. Here I've only focused on models that suppress small-scale structure, right? All these curves I drew go below the CDM example. There are also lots of interesting models that lead to enhancements of power on small scales. But what I want to do is show you a specific example of how we can use an observation of small-scale structure to actually place constraints on these models. Okay, any questions before I go further? So two shows up, so for light particle mass? Yeah, so for sufficiently light particle masses, this cutoff comes on large scales. So for most of the dark matter models we consider, the mass is so large that this cutoff would be way off the right-hand side of this plot at extremely small scales. But if you crank down the mass, then you push the cutoff to the left towards larger scales. So it doesn't amplify. This is the way to think of this is as sort of an interference effect. So because there's a large de Broglie wavelength in these models, the waves, you can think of the dark matter field as being a superposition of waves that sort of interfere with each other. Right? Yeah. Okay. So what's one way we have to observe structure? Yeah, one more question.
Very naive question.
Yeah.
What are you denoting with H here? Some normalized Hubble constant or something?
Yes, yeah, just a normalized Hubble constant, yeah. It doesn't matter so much for this purpose. Yep, question?
So both in your cosmic microwave anisotropy and this, you're drawing a few oscillations, but they're not too many. What determines the number of oscillations?
Good.
If it's not a critically damped problem, because you see right away it seems to be less than that. What determines that? What physics determines
Yeah, good. So in the CMB case, I erased the plot, but the reason that the higher order oscillations are washed out is because of essentially of photon silk damping, right? So the photons are free streaming on small scales, and that wipes out the perturbations. There's essentially similar physics here. So for modes that entered the horizon very early, the dark matter is so tightly coupled to the photons and baryons that no structure forms at all, right? It's only once you start to form structure that you see these dark acoustic oscillations imprinted. Yeah. Good. Okay, so I'm going to focus on another galaxy, this time our own galaxy, the Milky Way, because this provides us sort of a testing ground for these different models of dark matter. So the Milky Way is, in terms of stellar mass, a fairly typical spiral galaxy. It lives in a dark matter halo that has a mass of roughly 10 to the 12 solar masses. And surrounding the Milky Way, we observe other small galaxies. For example, in the southern hemisphere, we observe the large and small Magellanic Clouds. Just to give you a sense of scale, the Large Magellanic Cloud has a total mass of about 10 to the 11 solar masses. And over the last 20 years, we've discovered, and in fact, several folks in this room have helped to discover kind of new population of extremely faint galaxies that are orbiting around the Milky Way. So you can think of these instead of sort of standard disk galaxies, these are really just collections of stars. They're extremely old metal poor systems that formed early on, and they're stars we observe today as kind of remnants of that initial burst of star formation. And these are sort of sprinkled throughout the extent of the Milky Way's dark matter halo. We now know of roughly 60 of these dark matter-dominated dwarf galaxies. And what I want to show you is a fairly simple way to understand what halo masses they occupy, right? So what I'll argue is that the smallest of these galaxies that we observe occupy dark matter halos with masses of roughly 10 to the 8 solar masses, pushing us into this interesting regime of dark matter physics. Before I move on, I want to say that the prediction from models like cold dark matter is that there's actually an abundance of structure on small scales, so not just these dwarf galaxies whose halos we can actually see, but also many tiny objects that probably remain completely dark, right? And so one of the observational frontiers is actually robustly detecting the existence of these galaxy-free dark matter halos. We don't currently know whether they exist or not, and I'll show you a few ideas for how to do this. Okay, so the Milky Way, as I said, is a specific galaxy. Actually, there's a synergy here with what came up last week in the plasma talk. We can't model a kind of ensemble average of a theoretical galaxy. When we do the Milky Way, we actually have to model its specific dark matter structure and substructure. So to do this, we run numerical simulations, essentially n-body and hydrodynamic simulations of structure and galaxy formation. And one of the predictions from these simulations is known as the halo or subhalo mass function. This is essentially counting the number of these tiny clumps of dark matter that are orbiting within the Milky Way. So in a CDM context, a robust prediction for this cumulative number of halos is that it rises towards low masses. The slope of this rise is roughly inversely proportional to the halo mass if we plot it cumulatively like this. And of course, if you change the physics of dark matter, then you have a different prediction for the number of these tiny halos. For example, in a warm dark matter universe, there's a characteristic cutoff in the number of small halos, right? So this cumulative curve flattens. Now, this is not what we observe, unfortunately. It's very difficult to measure the dynamical masses of these tiny galaxies. We do have such measurements, but they probe only the very, very inner regions of these halos, right? It's difficult to get a measurement of the total halo mass for these objects. But what we can do is think about the distribution of the stellar masses for these galaxies that we do observe. So this plot is set up in a similar way, right? Cumulative number of tiny galaxies orbiting around the Milky Way is a function of stellar mass. So we've observed, as I said, roughly 60 or so. We know that these observations are not complete, right? There are tiny galaxies that we can't currently detect due to the limited sensitivity of our telescopes. Upcoming facilities like Rubin will really help with this. So I'll also, just for reference, plot a completeness corrected number here. So we know roughly 60. We expect in total, with a big error bar that we can debate later, roughly 200 of these tiny galaxies. And so what you can do then is, very naively, match the cumulative number of these galaxies that we see with the cumulative number of dark matter halos we predict in a given model, either using the observed number or the completeness corrected number. And what this gives is an upper limit on the halo mass of any of the galaxies that we currently see. And it turns out that given the current observations, which, as I said, have really drastically improved over the last decades, this upper limit on the smallest halo mass of any of the galaxies turns out to be about 3 times 10 to the 8 solar masses, right? And of course, to actually derive the limit, we do something much more sophisticated than this, right? We actually forward model the satellite population, including the contribution of the Magellanic Clouds, accounting for the incompleteness correctly. But this is, from that full analysis, the actual 95% confidence result. So this corresponds, if you do the mapping, to a wave number of about 50. And what I've argued is that we observe structure on these scales, right? On the scales of halos of roughly 3 times 10 to the 8. So a way to think about this is that we place a lower limit on the amount of power that's centered right around this wave number of the minimum halo mass that I showed you. And that's just because these mass functions are steeply rising towards the faint end, right? So most of the halos we probe are in a fairly narrow mass range. So this is interesting. This leads to a number of constraints. For example, on the mass of the fuzzy dark matter at the level of 10 to the minus 21 electron volts, that's an order of magnitude stronger than the kind of canonically invoked 10 to the minus 22 electron volt fuzzy dark matter. But beyond the constraints, I think the more interesting point is that we're actually starting to map out in more of a model-independent way how much structure there is on these scales, and therefore we can make statements about a wide variety of dark matter physics. So hopefully I've convinced you of that. I'm going to move on to the last part. and talk about how we can probe these entirely dark halos, right? The technique that I just showed you is fundamentally limited by galaxy formation, right? Arbitrarily small halos can't form galaxies, but there are ideas to probe even smaller objects. I'm going to draw the Milky Way again, but this time in a different context. So if we imagine, for example, a globular cluster or a dwarf galaxy as it orbits around the Milky Way, it will be stretched out into a long and thin and generally pretty dynamically cold stream of stars, right? And this process of tidal disruption is generic. We observe lots of these streams around the Milky Way, now over 100. And the idea is to use these streams as essentially dark matter subhalo detectors. So imagine a tiny dark matter halo, whether or not it hosts any stars, orbits close to one of these streams, sort of passes through. Then what folks have shown, and as again, including many folks in this room, is that these gravitational perturbations from the small subhalos can leave characteristic gaps and distortions in the density structure of stars along the stream. So this is one way to kind of go below this galaxy formation threshold and start probing the regime of completely dark halos. There are lots of other techniques we're discussing, including strong gravitational lensing and so on. This is, what we're all here to do, is to kind of hash out these different techniques. Okay, so just to wrap up, I want to hopefully motivate you and communicate that there's lots of exciting observations coming in the near future that will help us with this problem of dark matter structure on small scales. So one way to kind of think about this landscape is in the parameter space of redshift. So here I'll plot time going this way, so present day today. And on the vertical axis, I'll put this wave number. So now smaller scales are going towards the top of the plot. So what I've shown you, this technique of essentially counting small dwarf galaxies, lives in this region of the parameter space, right? So this is the region of near field cosmology, where we're doing these observations in the local universe. And I mentioned earlier that Rubin Observatory, so the LSST survey, is coming soon. We expect first light within the next roughly year or two. And what Rubin will do is expand, drastically increase the number of these tiny galaxies and stellar streams that we observe around the Milky Way, allowing us to make this sort of limit a more robust measurement, right, at small scales. Rubin's, of course, not the only thing that's coming. So there's the Roman Space Telescope, which will help us both map out structure in the local universe, and we'll discover lots of strong gravitational lenses. So there's a sort of complementary region of parameter space here, probed by strong gravitational lensing, actually also including JWST. There have already been analyses of JWST strong lensing data that are starting to push towards these interesting halo masses of 10 to the 7 or even 10 to the 6. And this picture is complemented by a whole bunch of other things, some of which I will attempt to draw. So there's a region of the parameter space where we can observe galaxies, and in fact, I won't limit it to low redshift, right? So including with telescopes like JWST, we can start to count relatively faint galaxies, even going towards higher redshifts. And these probes sort of fill in what was traditionally probed in this parameter space using the cosmic microwave background, CMB lensing, and the Lyman alpha forest. One interesting chunk here of the parameter space that is already starting to be covered by current experiments is that of 21 centimeter cosmology. This has been the focus of some of our discussions. There are active experiments going on in this regard. For example, Hera is analyzing their data, and we may be able to start probing structure in this sort of higher redshift but still fairly small scale range soon. Okay, so just to wrap up, hopefully I convinced you that the small scale structure contains a lot of really intriguing hints about the physics of dark matter. We hope to actually start placing measurements in this regime of completely dark halos soon. I would bet on this happening within the next 10 decades. I guess this is within the next decade. Sorry. Within the next 10 years. Yeah, so I guess, we can check. This is being recorded, so we can see whether my bet pays off or not. I think the interesting challenge that we have, which I'm happy to discuss more, is how to kind of combine all of this really rich information that we're getting, particularly because a lot of it is highly nonlinear, in the highly nonlinear regime, right? So to actually do this modeling at the level of precision, right, that places small scales on the same footing as large-scale cosmology, we have to develop really robust simulation and modeling tools, and that's one of the things we're working on here. Okay, so I'll stop there. Thank you very much.
Some years ago, there was a discussion of cusp, the center of galaxy, interacting dark matter. You didn't discuss that at all.
Yeah, good. No, not at all. So I should have said I focused here on purpose on dark matter physics that affects the linear matter perturbations, essentially. But the question of whether there's physics beyond CDM at late times is still very much alive. So one example that a lot of us are actively working on is that of self-interacting dark matter. And that, I would say, that discussion has evolved into a sort of interesting place, right? It's no longer just a question of whether the halos are cuspy or chord. It's now more of a question of reproducing the entire diversity of galactic rotation curves that we observe. And one conclusion that's becoming clear is that in order to explain systems going all the way from the largest clusters down to the smallest dwarfs, the self-interaction cross-section, if it exists, should be velocity dependent, right? It should reach fairly high amplitudes at small relative velocities while remaining consistent with the bounds from galaxy clusters at high velocities. So happy to talk about it more, but that's a brief overview.
Another very silly question. So you've drawn some data points with error bars on the left-hand side of the plot. What exists for the right-hand side, if at all?
Good.
Yeah, sorry, go.
So, okay, I don't want to, there are several people in this room who have worked on the right-hand side of this plot, so I want to be very, very, very careful with what I say. I think in terms of model-independent measurements, just of putting an error bar on P of K, not much. There have been a few strong lensing analyses that look at this. We're very interested in doing this with the Milky Way satellites and so on. But I think mainly what we have right now are analyses in the context of specific models that place limits on the power.
So speaking of which, that was my follow-up question. You have limits on these ones where they're bounded by the CDM model. What limits, if any, do exist from the other side?
Yes, good. So the other side is quite interesting. If you push the power to extremely high amplitude, so way above where I can plot here, then there are limits that come in from other dynamical processes beyond just the formation of structure. So for example, the dynamical heating of stars in dwarf galaxies. In terms of structure, it's, I would say somewhat probe dependent still. So doing this exercise that I showed you for the dwarf galaxies from the other direction is much more difficult because there are degeneracies with the astrophysics of galaxy formation in those small halos. That's not universally true for all probes, but I think that's the current status. Yeah.
When you're talking about the perturbations of stellar streams by dark halos or strong lensing, maybe some kind of perturbations in the lenses created by dark halos, black holes could also be significant perturbers, and in some cases actually even more sort of pronounced than dark halos because they're much more compact. So what do you think about breaking the degeneracy between black holes on the one side and dark halos on the other side when it comes to stellar streams or strong lensing and similar observations?
Yeah, good. So I think for astrophysically produced black holes, the game there will really be in the statistics, right? Because we predict in these models an entire spectrum. I erased the halo mass function, but a really large number of these tiny dark clumps of dark matter, and those will outnumber the perturbations from the black holes, right? Of course, in specific systems, it's hard to interpret.
What if there are primordial black holes or intermediate mass black holes that are numerous?
Yes, good. So I think, yes, good. My answer changes slightly if the black holes, if we're thinking of a population of black holes that accounts for part of the dark matter. In that case, well, there's a lot of work on this. It's difficult to reconcile this with all the data that we have, including microlensing, if the black holes are only of one mass. Right? Now, of course, you can invoke some kind of mass spectrum of black holes, and maybe it only accounts for a fraction of the dark matter. So I think the answer to your question is yes, this is part of the physics we're probing. But we want to use the full range of predictions from models of structure formation to disentangle the halos from the black holes. Yeah.
I have a question about interactive dark matter. So obviously, I think we don't see the wavy pattern in the distribution of galaxies with some constraints, and we also have presumably some constraints from the direct detection experiments. So my question is kind of which is stronger, or kind of is there a regime where it becomes probably the same cross sections?
Yes. So for these kinds of models that affect structure, on dwarf galaxy scales, there are constraints from direct detection, but those constraints are strongest for relatively high dark matter masses. So dark matter masses above a GeV, if we're considering the dark matter to scatter off of protons. The nice thing about these cosmological limits is they actually don't care about the mass of dark matter, even if we have, let's say MeV or tens of keV dark matter particles that scatter off of protons, this argument still applies. So there's complementarity in that sense, right? They're probing different parts of the parameter space, right? Yeah.
Can I just add on to that statement? So direct detection is going to not be like a true upper limit. They're going to have sensitivity loss when you get up to really high scattering cross sections, because they're deep underground. And so dark matter particles have to traverse the atmosphere, have to traverse the Earth. And if there's really a lot of scattering, then they lose a whole bunch of kinetic energy. They may not make it to the detector. They're certainly not going to make a signal. So there's a ceiling to that.
Yeah.
So this kind of goes above that ceiling.
Yeah. I mean, maybe one thing for context is that these interaction cross sections are much larger than what we would think of for WIMP, canonical WIMP dark matter. These are tens of orders of magnitude stronger interactions. Yeah. Yeah, that's certainly true. I think, yes, well, we should discuss this. There may be interesting sense in which if the dark matter strongly self-interacts, we do expect signatures in the power spectrum as well, right? In addition.
In the power spectrum, yeah, but not with direct detection.
Yes, yeah, certainly, yeah.
Do you see a role for direct acceleration measurements in any of these constraints?
Oh, interesting. Yes, so people have been thinking about this, particularly in light of Gaia, right, and the measurements we've gotten of stars in the inner galaxy. I think the challenge is that those measurements are best very locally, right? So it's great to really precisely measure the local dark matter density, but connecting it to this cosmological picture, I would say, still remains difficult. Yeah, but it's a very interesting way to go, and I think it complements what I've talked about. Yeah.
Thanks, Mr. First of all, and I apologize if this question is not what you expected. So I know you give a very nice spectrum about all the dark matter model, but there's one thing you did not cover, and I don't know if it's still people discuss, is modified internal dynamics or not. Personally, I don't know much about this, and I'm not a theorist, but I want to bring this up as a theory kind of discussion. So I thought it was pretty much bad because it cannot explain the CMB, but from last year, which is the 40th anniversary of MOD, people were saying that they can. I met some people from MOD and they say they can explain the CMB, which I don't know nothing about that. So I want to know if we can comment on some of that, because that is definitely a thing when we talk about dark matter and didn't mention at all. So if we can comment on some of that.
Okay, so now I'll be even more careful. I mean, I guess what I'd say is that, so yes, so the zeroth order thing is it's difficult to explain the full spectrum of observations that I just showed you. I'm sure that people can cook up theories that do this, but I think then it also becomes a question of elegance, right? I mean, there are not very many ingredients that I showed you that are necessary to explain both the CMB and the large-scale structure today in the context of dark matter. I think it's fair to say I've yet to see a similarly simple description from the context of just modifying gravity. Right?
So it's not, I don't mean to say that that's, you know, I'm not against it, but just that doesn't actually tell you anything about how you would get from the linear regime to the nonlinear regime. And it's very unclear whether that's really feasible. So there have been some general statements about how difficult that is. I think the general statement is you need non-locality and you need some really interesting model building to accommodate what we know about large-scale structure from the linear regime to the nonlinear regime using model. Please.
So I have another naive question, kind of Kavli's question. Is there, presumably all these lines, all these different models go to zero, is there like what's the smallest scale where you can differentiate between the models?
Right.
See, like, Helios theory.
Yeah, so I mean, I think with current data, it's somewhere around here. You know, we can plus or minus a factor of a few. In principle, I think we don't know the answer to that question, actually. I mean, there will be a scale where the structure formation is limited just by, for example, the mass of individual dark matter particles, but that, in general, is on much smaller scales than what I've plotted here, right? I don't think the line has to go to zero in general, right? I mean, if we just at some level have a bunch of particles, then there's essentially like a white noise contribution to the power spectrum, which, you know, just either, depending on how you plot it, either plateaus or rises at small scales. Yeah.
Yeah, maybe just to add on to that, if you start seeing some kind of suppression there, it actually gives guidance to a lot of the terrestrial experimental searches. So you may, with cosmology, not be able to tell whether it's a sterile neutrino or some kind of fuzzy dark matter particle, but if you give a mass range to an experimentalist, it makes their job a lot easier. So they can design an experiment that rather than having to cover some very broad range of parameter space can be targeted on a very specific range, and maybe you build 3 different experiments